So we've got our radical lecture to get covered here. When we talked about our alkanes, and we've yet to talk about our alkenes, but this will tie in nicely. When we looked at our alkanes, what we had as far as our bonds was just carbon to carbon and then carbon to hydrogens. Those types of bonds are nonpolar, not a whole lot of reactivity out of it, and we came up with London dispersion forces, low melting points, boiling points, and no reactivity as far as we were concerned. Well, it turns out we can get them to react if we introduce radical chemistry into our vernaculars. So where have we seen or where have you heard free radicals before? You might have heard of oxidative damage due to free radicals and everybody trying to take special pills and medicines so that we can eliminate radical reactions from our bodies. It's a bit overdramatic, but it's kind of true. All a free radical is an unpaired electron. So if we go through and take a look at some of the structures, we've got unpaired electrons in each of these structures, okay, all showing varying radicals. That first one is a started from a peroxy structure, and what ended up happening is a bond broke in such a way that the electrons went back to their assumed atoms, which meant that we ended up with that unpaired electron. The middle one, interestingly enough, is actually another way to represent the molecule of oxygen that we breathe every day. Turns out oxygen exists as a diradical, which is what makes it kind of dangerous and why we get high energy free radical oxygens floating through our bloodstreams that we want to watch out for. It's also one of the reasons why we can actually use it in most cases because of this reactive state. Another common one that you'll see floating around is a bromine radical. We'll use that one for synthesis, as we'll see later on through this lecture. And then that last one is a carbon radical that we'll see as an intermediate in a variety of different stages, and we'll want to evaluate something about its stability. So when we look towards our stability and reactivity, what makes a radical reactive is the fact that it's missing an electron. Well, we've seen that before with carbocations. So we can approximate radical stability towards our carbocation stability. So kind of keep that in mind when you're trying to decide on if you've generated a stable radical or not. They will react very quickly with the most available electrons possible. There's a variety of ways that we can look at available, so that one becomes a little bit trickier to work with. And what we're looking at is reacting nonpolar bonds, most typically. Okay, because polar bonds, we've got other easier methods to take advantage of for our radicals. Okay. So how do we get this started? Well, to get our radicals, we're first going to have to initiate them. So there's always an initiation or a radical initiation for all radical reactions. So you'll see this pop up and you'll look at an individual reaction and be expected to know that that was an initiation step as opposed to one of the later stages. The initiation is started with either heat or light, and what ends up happening is that heat or light is enough to excite a nonpolar bond, a very high energy nonpolar bond that actually causes it to break open. Sorry, a low energy nonpolar bond. So lower energy requires less energy to excite it, and hence it can break open. We won't see this happen very typically. Like a carbon-hydrogen bond is actually relatively high energy. Where we're going to see it is in situations where we take two very electronegative elements and we bind them near each other. So in our top example, we've got an oxygen to an oxygen, and the bottom one bromine to bromine. In both cases, those are very electronegative elements that want to take electron density away, but we've now partnered them with the same element. So now they're both equally pulling on their electrons, trying to get their electrons back, and that's what's going to result in our homolytic bond cleavage. So what ends up happening is we take a look at those electrons in the bond. We'll start with our peroxy structure. To get that line, we have two electrons. Well, a homolytic cleavage means that we take the electron from one of those bonds and we put it on our one oxygen, we take the electron from the other one and we put it on our other oxygen. You'll notice that the arrows that I've shown here only have one head. So when we're dealing with radical reactions, we're going to be dealing with half-headed arrows, which is kind of the long way to say this. That should be arrows. Or you may hear it also as fish hooks. Okay? So what we're trying to show is, again, how that bond, where those electrons went when the bond broke. Because it's such a low energy bond, heat or light is usually enough to cause that bond to homolytically break open, and the result is we end up with now no more that bond. So you'll notice that we don't have that bond anymore, and in the case of our oxygen example, we'll end up with two of the exact same piece. Okay? When we're doing our radical initiations, we usually do this in such a way that we end up with our radicals of being the exact same, because we don't want to generate two different radicals, because two different types could potentially do different things. And if we're going to run a reaction, we want it to be as consistent as possible. So you'll notice again we've got our radical sitting on the end of it. This radical happens to be resonance stabilized. We can push it in to form the pi bond, and we can break the other pi bond open. And we now have a resonance stabilization for our radical structure. So now that we say, okay, well, that radical is okay to form because it's resonance stabilized. So that's actually an evaluation of its energy. The other common way we'll see our radicals used is with bromine, or really with any of our halogens, and we'll talk about limitations on that, but bromine's the characteristic example. And in the case of bromine, we'll use light as our energy source, and that will cause our bond to break homolytically, again with our half-headed arrows, and we end up with two bromine radicals. Okay. Once initiated, now our radical can go through and do its secondary chemistry, and that would be our propagation step. So, as far as identifying our radical reactions, what you want to do, identify your initiation. It's the formation of radicals. So start with no radicals, end with a radical. Red flags, you will see heat typically, or light. The heat may be written as a delta, light may be written as H nu, or written out as light. The other big signifier is that we're looking for an oxygen bond or a bromine bond. The bromine is relatively simple and kind of stalls out with just bromine. As you might remember with oxygen, it needs two bonds, so it's almost always connected out to something else. That could just be carbons, or in this case it could be those carbonyls. So we're looking at our initiation of our radical reaction. Once it's started, we can then look at how the radical can react with other structures. The one we're primarily concerned about is with alkanes. Alkanes didn't have any site of reactivity beforehand, so we're going to have to somehow get them to react, and that's where our radical is going to come in. So our radical is now floating through our solution, trying to find a source of electrons. The first thing that it's going to bump up against in this random solution is probably going to be a hydrogen. Probably not going to be able to get into the carbons, because the carbons are buried behind a bunch of hydrogens. So in an individual propagation reaction, we're typically expecting our bromine to bump into that hydrogen, which means it's going to need to form a bond. It needs that extra electron. Well, the only place it can get that electron is from the bond between our carbon and hydrogen. So what we're going to go ahead and do is, again, use a radical mechanism. We're going to take the electron from our hydrogen and the electron from our bromine and put them together. You'll notice that the arrows in this case are going into the space between the atoms, whereas in our previous mechanisms with our heterolytic cleavage, we took pairs of electrons and we drew them to our positive atom. Okay? And that's because we can't show the arrow going to the space, because then it's not clear where the electrons are going. In the case of radicals, because we're showing an arrow from both ends of the bond formation, it's okay, and we can show it going into that space in between. So it's a slightly different format, but we're allowed to do it because of our notations. What happens to that last radical, or that last electron, which I'll now highlight in blue? Well, where it's shown right now is in a bond, but to have a bond there has to be 2 electrons. We took one of those electrons away, so it can't be in a bond anymore, so we'll have to specify where it goes. It will go back to the atom from whence it came. And we end up with, as a result, the product on the far right. Okay? Our radical is now on a primary carbon. The bromine could have just as easily gone to the other hydrogen, so we can use it in different colors. It could have taken an electron from our other hydrogen that's shown on there, in which case our bond is going to break again homolytically, and our electron is going to now sit on our secondary carbon. So we end up with 2 possible products in a radical reaction, or at least in this radical reaction. And our end result will be HBr. You'll notice the HBr is no longer a radical because we paired the electrons. We're forming a bond between the bromine and our hydrogen. And we're breaking the bond between the hydrogen and the carbon. That bond gets broken. Okay? So, we've got the HBr, we have radicals again in our product. This is where this reaction gets a little bit interesting, because we now have 2 possible radicals. Well, which radical is favored? Well, think back to what we said our radical reactivity was based on. It's based on carbocations, missing an electron. So where is a carbocation more stable? Secondary or primary? Secondary, good job. The main product that we see in the case of the bromination is the secondary radical. We don't see the primary actually show up, at least to any large amount. This is a propagation reaction because we started with a radical and we end with a radical. It's a different radical, but that doesn't matter. As long as we start and end, we're okay. Other forms of radical reactions, you'll notice in the next line down, I decided to start with one of the carbon structures, and now I'm going to react it with neutral bromine. Same ideas that we had before. Our carbon radical needs electrons. Bromine will supply it. Whoops, let's fix that arrow a little bit. The bromine bond will supply 1 electron, but then we got to piece the other one over. Okay, and what we end up with is a neutral product with bromine now substituted onto our structure. Well, remember what we started with. We started with this whole thing with an alkane. So we converted an alkane to an alkyl halide. Okay? That's the biggest lesson to pick up out of the radical chapter. We can now convert non-reactive alkanes into reactive alkyl halides. The halogen that we end up doing the substitution, or we will substitute a halogen for the most substituted hydrogen position. Okay? So we're doing a free radical substitution reaction. So now for our next test, we've got acid-base reactions, free radical substitutions, substitution type 1, substitution type 2, elimination type 1, elimination type 2. So we've got 5 different mechanisms that you need to understand when you go through and look at these problems. Along the lines of this mechanism, you'll notice that each step, instead of requiring 2 arrows, like in our standard substitution or eliminations, we'll have 3 arrows per step. And that's because we have to account for every single electron, and it has to be single electrons because it's a radical reaction. Okay? So take a moment here, pause, and add the arrows to that last reaction. So pause now. And we're back. So what are we going to do for our radical here? We'll take our radical from our carbon, radical from our bromine, and we've now added our arrows to show the formation of our new product, and we would end up with the primary bromine structure, our primary alkyl halide. Again, if we were going to look at how much of each of these products was formed, we would expect our secondary to be in much larger concentrations than our primary because the intermediate was much more stable. Same idea as our carbocations. Which is what this next slide is suggesting. Which product is favored? The product that's favored is going to be the one that generates, whoops, sorry about that, the one that generates the most stable intermediate, which is our second reaction, or really our second product situation, which comes back to our first reaction, our secondary radical. Bromine is very, very, very selective. We're going to generate the most stable radicals that we possibly can throughout the radical reaction with bromine. After we've gone through and started to form this, you'll notice even in that propagation step, sorry for the back and forth, we still have a radical. That radical can continue to react and continue to mess with different things. So when we're going to stop the reaction, we have to add in some kind of species that goes through, scavenges the radicals, and stops their reactions, so that we no longer have products potentially forming out of this. The only way that we can get rid of radicals is to have radicals combine with each other. So in that first reaction, we're taking two radicals, we put the electrons into the space between the atoms to make a new bond between those two atoms. It does not have to be a bromine and a carbon radical. As we see in the third example, we could take two carbon radicals to make a massive new carbon structure. This is actually one of the reasons why I don't like radicals, because we can generate a whole bunch of random junk that we didn't actually intend to set out for in our initial attempts. That said, if we have an alkane and we need to get it reactive, we have to run a radical reaction. So we don't have a whole lot of choices. They are ridiculously helpful to increase reactivity, but the issue is we end up increasing a bunch of other things. So our yields can sometimes be a little bit questionable with them. Those yields are ultimately determined based on concentrations. If I generate a whole bunch of my carbon radicals, then I might expect a much larger yield of the dicarbon structure. But if I've got a very dilute solution, the odds that those two carbon radicals combine with each other are very, very limited, and we don't see any of that product forming. Okay? So a lot of our radical chemistry has something to do with stability, but we're also going to see a pretty big contribution from concentrations as far as overall products go in the grand scheme of things. Sometimes we can also incorporate a scavenger, some kind of terminator radical to go through and scavenge and react the remaining radicals. The big lesson with this is our termination reactions for radicals result in the loss of a radical. So we have to start with a radical and then look at our products and not have a radical. So the utility. Do alkanes have any reactivity? No. So if I started with methyl cyclohexane and wanted to turn it into an alkene, before we looked at radicals, I got nothing. There's no way to run this reaction. After I now understand that I can react it with a radical, what I can go through and do is do, at this point, bromine in the presence of, say, light. And what will end up happening is that will cause a substitution for a hydrogen at the most substituted position, which happens to be here. I now have a tertiary alkyl halide. Okay, so that would be my first sequence. Okay, my first step, Br2 and light, which gets me my tertiary alkyl halide. Okay. So what happens in that next step? Well, look at your reactant and product. We have to be running some kind of elimination reaction. To run the elimination, we're either running E1 or E2. It's a tertiary alkyl halides, so that means E2s are out the window. Or, sorry, yeah, well, actually no, that means both are valid options. Right? So if we want just the elimination, we want to make sure that we don't have an E1. because the E1 is going to directly compete with the SN1. E2 is going to be okay. We don't have to worry about sterics because what we're trying to form is the most substituted double bond. So that is absolutely fair game. So what we'll go through and do to push an E2 elimination means for that 2 type, I need a strong, so that strong should pair with the 2 base. And that base will pair with the E for my elimination. So, strong base, I can pick pretty much anything I want. I will pick methoxide. As far as the test goes, that would be a perfectly valid answer. Though you could see, at least in a multiple choice, the option of sodium methoxide, because we don't like seeing that negative charge, and we would usually see the presence of a solvent in the presence of methanol. Almost always we'll see those two tied with each other because they're related. Right? To get the methoxide, we have to have methanol. So what we've gone through and done in this process is we converted an alkane to an alkene. Kind of cool. So that's the idea behind organic chemistry. Start with something, can change its structure, continue to change its structure until we end up with a target compound. Okay? So that's what we'll use it for. If you see an alkane, immediately, radical reactions. That's your lesson. So with those reagents, we can use bromine, and you'll notice that I didn't talk about any others. But we do have the option of using chlorine. We do have the option of using chlorine as a reagent, and that is about it. Okay, it's just chlorine and bromine. Typically, you will only see bromine used. Okay? And the reason is for that very tail piece. Bromine is selective, meaning when I run the bromination with that above species, what I get in the case of the bromination is the bromine at the tertiary position. Chlorine generates a much more reactive radical, okay, which is a good kind of short answer question. Why might the chloride or a chlorine generate a much more reactive radical? I'll leave you to think about that one. It becomes so reactive that what we end up seeing is chlorination potentially happening at the most available sites. So anything on the outside of the structure are possible positions. We'll still see single chlorination, so don't get me wrong in this case, but what will end up happening is we could end up with that product. We could end up with this product. We could end up with the tertiary halogen. So we end up with so many different products that are all now based on concentration and amounts of hydrogen that we don't get a single product, not very selective, not very useful synthetically. Okay? So our chlorinations don't work out very well for us. We won't really see any other types of radical reactions beyond our halides. So why not use fluorine or iodine? Well, both of those do potentially work. Fluorine, similar to chlorine, generates a very unstable radical. That radical is actually so unstable that the reaction happens so fast that it's actually explosive. Not a good option to have in the lab. So we won't use fluorine as a radical initiator. Iodine, extremely selective, much more selective than bromine even. The problem with it, however, is that that reaction is ridiculously slow. We generate a super stable radical. That radical is so stable it does not want to react with the carbon to actually generate the carbon radical to push further on through the intermediates. That means when it comes to our reagents and radicals, at this stage in the game, bromine is your winner. So stick with bromine for your eliminations and you should be set. Your textbook is going to go through and start to discuss why bromine versus chlorine becomes out better, and it has to do with transition states and energy diagrams. The short of it is that when we look at the bromination reaction, we are generating a endothermic HBr, stronger acid in that intermediate stage, versus HCl, which is a weaker acid, which means we have a lower energy for that intermediate structure. So the result is, for bromination, we have an endothermic reaction. For the chlorination, we have an exothermic reaction. The endothermic is much more selective than the exothermic. If you want more on that, check your textbook. Lesson learned, do bromine. So yeah, choose bromination. Stereochemistry, if we went through this reaction, let's see, did I actually give you the product? Nope. If we go through this reaction, what's going to be the result? Well, we said our bromine is selective. It will do a substitution for the most stable or most substituted hydrogen, so we'll end up putting a bromine here. Interesting feature of that product is that we now have a stereocenter at that carbon. And if we have a stereocenter, we should be concerned about whether or not this is an optically active product and all that other fun jazz. Well, with our radical reactions, due to the process of us starting with an achiral starting material and achiral reagents, that means our final product mixture, this is where we're going to be a little bit careful, our product mixture will also be achiral. Okay, that doesn't mean our product is achiral, that means the mixture is achiral. So, said another way, what we end up having to generate with our product is two products. We would have the wedged bromine and we would have our dashed bromine. Those are naturally going to fall out of our radical mechanism. So when it comes to stereochemistry, we will still end up with two products because of this kind of radical issue. If we start with an optically inactive starting materials, we will end with optically inactive. Okay, so we'll either end up with achiral or racemic products. In this case, racemic. The next issue, when we go through and take a step up from alkanes, if we add in a double bond, is that going to change the overall chemistry? Well, we would hope not, but it does. Okay, and what's happening with that really has to do with our intermediate. If we go through and look at our intermediate, we're going to pull off a hydrogen off of our secondary position, and the result of that, let's make sure I didn't lose any carbons here, is that radical. That radical can then pick up a bromine. Glad I left myself lots of space. And we got our bromine on that position. Why do we end up seeing that reaction? Well, that carbon is resonance stabilized. That resonance stabilization facilitates the alkyne radical reaction. Anybody notice an issue with this resonance stabilization? So let me draw that one, our first radical, a little bit higher. If we go through resonance with our arrow pushing, what's the net result of our other structure? Which is then going to result in what product? Double bond and bromine. Oh God, I'm glad I overlapped that. Are those two products the same? Nope. We still have two products. We have to evaluate this resonance option. Between these two options, neither one is more or less stable than the other, which means both are going to be valid options. If for some reason in the process of drawing this out we notice that we do have this resonance option but we resonance to a more stable radical, that one is going to drive the possible products. A little bit irritated that I didn't stepwise that bottom thing in there. And I really didn't, did I? Oh, nope, I didn't. Sorry. What do I mean by the resonance stabilization? Well, let's drop in that double bond. or drop in an extra carbon. If we drop that carbon in there and we look at our intermediate, what we'll end up with, yep, and our other resonance stabilized structure will be here. What we'll end up with for our products would be two bromination products, but one will be the major product, whoops, and one will be the minor product. Which one is the major product, top or bottom? We end up seeing the bottom being our major product, because if we go back to our intermediate, we have a tertiary allylic versus a secondary allylic radical. The tertiary allylic is more stable. That's going to push the bromine product, or that product being our major product. Okay, so we will have to watch out for resonance showing up with our radical substitutions. Thankfully, not the other one. What's the other R? Rearrangements. We'll just have to worry about resonance. Almost done, I promise. The next issue that we're going to run into with this is that if we want substitution to occur in this reaction primarily, we want to make sure that we limit the presence of bromine, because the alkene of our starting material can actually act as a good nucleophile. That nucleophile can actually share its electrons with bromine, and we end up doing an addition reaction. If we don't want the addition reaction to occur, we have to control the amount of bromine present so that we can actually wait for the radical formation. Once we have the radical, everything's good. Okay, so to do that, we can use a reagent known as N-bromosuccinimide. N-bromosuccinimide, or NBS. The structure is shown. Okay, so what will end up happening in this case is we still have that extremely, I don't know why I said extremely, we have that bond between two very polar or electronegative elements. With light or heat, we see that homolytic cleavage of that bond, which will generate the bromine radical. That bromine radical can go through with another bromine radical and form Br2 in small amounts, or it can go through and react as a bromine radical would typically to generate, sorry, that was an ugly arrow, in our standard radical mechanism. Okay, so the two reagents you're now responsible for are Br2 and light, or NBS and light. Okay, they're both going to be reacting with alkane type structures, and we're putting it in a radical substitution mechanism. So our radical substitution reagents, we've got them all listed out here. Bromine and light, and we're going to see a radical substitution with bromine substituting with hydrogen at the most substituted position. So pick a hydrogen that has the most carbons around it. We could also see chlorine pop up. It's just going to substitute hydrogen at pretty much all positions, so it's not as helpful to work with. The last one would be NBS with either light or heat. That's going to put a bromine that will substitute with hydrogen at the allylic or benzylic positions. Remember, benzylic is effectively the same thing as allylic. We're just not going to worry about this slide at all. It is in chapter 15, so if you look and see radical additions popping up, or HBr showing up as one of the reagents, then you can ignore that section within chapter 15. I will set up a separate lecture introducing addition reactions that I'll expect you to watch after the exam. So don't worry about that for exam 3. Which is still this. Yes, that's still with alkenes, so we don't want to look at that. That's still our additions. So that really gets us to the very end, our reaction summaries. This is going to be pretty much all the possible reactions that you can see on the exam. Please be careful. If you memorize this, you're going to have a bad time. Okay? Why? Because all we're really looking at is a carbon with a leaving group. The rest of that structure is added on there so that I can put in some extra information, like retention and inversion of stereochemistry, or the potential for rearrangements, okay, or rearrangement minutes, because that's a better way to spell that word. So that I can also push SN2s showing inversion. Okay, so we want to be very careful about the memorization process and focus more on what the patterns are within these structures. That we're looking at alkanes and their overall reactivity. Notice when the alkane reacts, we're putting the bromine at the most substituted position. When we look at chlorine, what happens? All sorts of crap happens. Okay? So that's a horrible thing to work with. So if I change the structure of the alkane, if you memorize that structure, you're going to not be able to answer the questions. So memorize the overall ideas behind these drawings, not just the structures. With the alkene functional group, you do not need to memorize that one or deal with that one or this reaction. You are responsible for the NBS alkene reaction. Okay? So that summarizes everything. If you've got questions, please feel free to send me an email. I will be posting at least one tutorial on a sapling homework question that a student has asked for. So please keep your eyes peeled either to discussion boards or to the announcements for more lecture videos. Good luck.